Hello guys, welcome back to the CCNA video series brought to you by ABY Design and Tech. In this video, we're going to have a look at Layer 2 EtherChannel. The objectives for this video will be to understand what Layer 2 EtherChannel is and why we need it. So to begin with, what is EtherChannel? Tell me, Abda, tell me. So, the technical term, it just allows us to take multiple physical links, bundle those links together into an EtherChannel, and then the switch will now see those links. Instead of being separate links, it sees them as one logical link. It sees them as one EtherChannel. And so when the traffic goes to actually forward traffic out of the EtherChannel, it will load balance that traffic across the physical links which have been bundled together based on MAC addresses, IP addresses, port numbers, etc. You name it. Now, can you see a use case for this? And you're probably thinking spanning tree protocol. So imagine this scenario. This is what would happen in a world with no EtherChannel. And that is a dark, dark world. So we have a single link running between our non-root bridge and our root bridge. That link is maxing out our 100% bandwidth utilization. So it's congested, so much traffic, network performance is poor. Now you're thinking, Abda, can't I just run another link between the non-root bridge and the root bridge? Surely that's going to alleviate the issue. I'll have two links running perfectly fine, but no, you can't. The reason being, spanning tree protocol. Spanning tree protocol is going to ruin the party. With spanning tree protocol, we can add that link, and it will make that link in block. So it will just put that link into the blocking state. Essentially, no traffic will be forwarded over that link, meaning we still have our same issue. Even though we've got two links now running to the same switch, we can't forward traffic over one of those links. We can have one link which we can use, the second link we can't use. Now, this is where EtherChannel comes in to save the day. So what EtherChannel allows us to do, imagine these two links here. We take those two links, we bundle them together, we put them into the same EtherChannel. Now, because they're part of the same EtherChannel, the switches now view them as one logical link. It views them as being part of the EtherChannel. So now, when the non-root bridge is going to forward traffic to this root bridge, it doesn't say, okay, I'll forward traffic over FA0/1 or GI0/2, etc. No, it says, I'm going to forward traffic over this EtherChannel. Then when it comes to actually forwarding the traffic, it's going to load balance and choose one of the physical links based on the load balancing algorithm. This is the power that EtherChannel gives us. It allows us to take multiple redundant links between switches and actually use all those links. So instead of spanning tree protocol coming in, ruining the party, in that it's going to block all of our redundant links apart from one. No, we can use all of our redundant links, forwarding traffic, carrying traffic at the same time. And that will be load balanced. So, benefits of EtherChannel, pretty self-explanatory if you ask me. Physical link redundancy between switch uplinks. So now we can have two links going between our switches. 2 links, 3 links, you name it. And so if this link goes down, no problem. I can still use this path. The reason being, I've got a spare link. I have a redundant link. Increasing bandwidth between switches. So instead of me having to resolve this scenario by buying 2 new switches with faster network interface cards, no, I don't have to do that. Instead, I just use an EtherChannel. I add multiple redundant links between my switches, bundling them into an EtherChannel. Now they're seen as one logical link, and guess what? I've increased my bandwidth because all I've done, I've added additional links, increasing my overall bandwidth. Think of it like this. Think of it as if we have congestion on a road. What do? We just introduce more lanes onto that road. It's as simple as that, because we can't increase the speed limit because that's going to cause accidents. No, we increase the number of lanes. So let's say we have a single lane. Then we split that single lane into 3, 4, or 5 lanes. The traffic is still moving at the same speed. However, more traffic can pass through because we have more lanes available to us. That's all we're doing. We're just increasing the lanes between our switches. We're increasing the links, allowing for more data to be sent overall at the same time. And so EtherChannel, think of it like this. It's as simple as this. Just take a whole bunch of links, combine them together, that's it, and then we've got one logical link. Think of it like this. Think of it as taking straws, wrapping a rubber band around the straws, and now those straws represent one straw, etc. That's exactly how it works. And the beauty of EtherChannel is that spanning tree protocol now sees those links as not being individual links, but as being as part of something bigger. It sees them as being part of the ether channel. So now when it blocks or forces traffic over a link, it blocks and forces traffic over the ether channel. And there can't be any loops. So there's no way that I'm going to be sending traffic over this link and then we'll loop back around this link. The reason being because the root bridge would be like, I haven't received traffic on FA0/1. No, I've received traffic on the ether channel. So that means I'm not going to forward it back over the ether channel. Imagine that was a broadcast frame. That sorts out our issues right there. Now, there are also some caveats, okay? So limitations, some limitations are ether channel, we're limited on how many links we can put into a single ether channel. So a switch can support more than one ether channel, and we're only allowed up to 8 links to be put into a single ether channel. And the links have to be between the same switches. So we can't do something like this. We can't put this link and this link into the same ether channel. Why? Because they don't connect to the same switch. This link connects to this switch up here. This link connects to this switch down here. So no, they can't be part of the same ether channel. However, these 2 links can, because they both end up going to the same switch. So yes, those can be part of the same ether channel. And then STP won't come and ruin our party by blocking one of those links. Now, even though traffic is low balanced over the links, it's not low balanced evenly. What you will see is when traffic is low balanced, you will see, let's say we have 2 links. One of the links will be more busy than the other link. And that is just purely based on how ether channel load balances traffic over the links. It's not going to be perfect. However, we will still get traffic shared between the links. So traffic will still be shared, but it won't be shared evenly. And in theory, we're not actually increasing link speed. So the links, let's say I combine 2 1 gig links into an ether channel. The links are still operating at 1 gig because the 1 gig defines how fast I can serialize or initialize bits onto the wire. No, we're not increasing the speed of the links, but we're increasing the overall bandwidth, because we're saying that we can use more links at once, which therefore increases the overall bandwidth, increases how much data I can send at one time, or how much data I can send overall over these links. So the way the ether channel works, we first have to identify what links we're going to put into the ether channel. Again, they have to be between the links have to be going to the same switch. Then we create the logical port channel interface. This is what the switch sees. So when the switch is going to forward traffic over an ether channel, it doesn't see the individual links, it sees the logical interface that we have created. It associates the physical links with the logical interface, meaning when I make a forwarding decision, I'm going to make a forwarding decision saying that I want to forward traffic over out this logical interface. And then when it comes to actually forwarding traffic, then it will use the load balancing algorithm to then pick which physical link it's actually going to forward the traffic over. So we create the logical port channel interface, and then we just assign the physical interfaces to that ether channel interface. And now any configuration we need to apply, we will apply it on the port channel interface, and then we'll then replicate that configuration to all the physical links which have been bundled into that ether channel. And as you can see, even from a configuration perspective, it's operating as a single link, a single logical link, because we're having to apply the configuration to a single interface. One thing to understand is we just can't take any links and bundle them into the same ether channel. No, the links have to all have some attributes which are the same. So port mode has to be the same between links. Access VLAN, trunk native VLAN, speed M2U, STP cost, STP port priority. So I can't do something like this. This will not work. This is not compatible. I can't combine an access and a trunk link to be part of the same ether channel, because they both operate differently. Access link, 1 VLAN, trunk link, multiple VLANs. However, I can do this. I can bundle these 2 links together, trunk links together, into an ether channel, providing that obviously they're the same speed, they support the same allowed VLAN list, and also they have the same STP cost. Now, there are 3 methods when configuring an ether channel. We have 2 methods, which are essentially 2 protocols, which allow the switches to negotiate. The switches talk to each other and be like, these are the links that I want to put into the ether channel. That's what the negotiation protocols allow them to do. Then we have what I like to call the brute force method, in that the on or the manual ether channel configuration we dictate. So we're not giving the switch a choice. We're saying to the switch, we're dictating the terms of the switch, saying to the switch, these links are going to be part of the ether channel, and that's final. And whichever method we use, whichever protocol we use, we have to make sure that it's the same on both sides. So if I use PAGP on one side, I have to use PAGP on the other side. If I use LACP on one side, I have to use LACP on the other side of the Ether channel. Now obviously, what I could do, I could have, let's say, a switch with 3 different Ether channels, and they could be using one could be using PAGP, one could be using LACP, one could be using the manual configuration, and that's fine, as long as the other side of the Ether channel is using the same configuration. So obviously, the configuration has to match on either ends of the Ether channel link. Now, let's talk about these methods. Port Aggregation Protocol, PAGP, is a Cisco proprietary protocol, and what does that mean? It can only be used with Cisco devices. And again, all it does, it allows us to choose and figure out which links should be part of the Ether channel. So the switches will actually have a negotiation, and there are 2 modes when we're configuring PAGP. Auto, which means, you know what, I'm going to sit back and relax. I'm going to wait for the other side to begin negotiations. I'm not going to actively hunt the other side and actively pursue the other side to form an Ether channel. And then desirable, I'm going to actively try and negotiate the other side and decide which links should be put into this Ether channel. PAGP allows for 8 active links to be part of the Ether channel. So I can have 8 links combined and bundled together into one Ether channel. And as you're probably guessing, based on the modes, it's similar to DTP, the dynamic trunking protocol, in that for PAGP to work, for me to negotiate and successfully decide which links should be part of the Ether channel and then form the Ether channel, one side has to be configured in the desirable mode. The other side, that can be auto or desirable, it's up to you, but one side has to be desirable. If we have both sides as auto, guess what? No links will be added to the Ether channel and there will be no Ether channel, because essentially both sides are sitting back, relaxing, and waiting for the other side to begin the negotiation process, and we don't want that. LACP, Link Aggregation Control Protocol, is an open standard protocol. What does that mean? It's vendor neutral. We can use it between Cisco and HP, HP and HP, Juniper and HP, Juniper and Cisco. And like PAGP, it's got 2 modes. Active, I'm going to actively pursue the other side and actively begin the negotiation process and say to him that I want to form an Ether channel. Passive, what do you think that means? You know what, I'm gonna take the laid back approach. I'm gonna wait for the other side to begin the negotiations of forming an Ether channel and telling me which links should be part of the Ether channel. Now, one of the main differences between LACP and PAGP, LACP, that allows for a total of 16 links to be bundled into the Ether channel. 8 links will be active, 8 will be standby. So that means is that if I have 16 links, and let's say I've got 8 active, 8 in standby or passive or whatever you want to call it, if one of those 8 links goes down, I can move one of the standby links into the active state. Simple as that. And active as in, not active mode, is active as in is actively participating in the Ether channel protocol. So I'm actively forwarding traffic over that link, over that physical link. Now, this is how it works again. So obviously one side of the Ether channel has to be active. It could be this side or that side, it doesn't really matter. And the other side can be active or passive. If we have passive on both sides, it won't work because they're both thin back. They're both waiting for the other side to begin the negotiations. So guess what? They're not going to be actively discussing or actively trying to negotiate which links should be added to the Ether channel. And then we have the last method, which is the brute force approach. And then we dictate to the switch, I am telling this switch that these 2 links are going to be part of the Ether channel. I'm telling this switch, these 2 links are going to be part of the Ether channel. I'm not leaving it up to you guys to discuss and decide. I'm dictating the terms to you. And this is defined by using the on keyword when we go and configure Ether channel. And whether we use LACP, PAGP, or manual configuration, we have to make sure that we use the same method or the same protocol on both sides. So if I'm using on this side, I have to use on the other side. If I'm using LACP on that side, I have to use LACP on that side. What you don't want to do is use on one side and LACP or PAGP on the other side. The reason being because these links will be forwarding, these links will be blocking, or in this case, both of these links will be forwarding because they're part of the Ether channel, and both of these links will be forwarding because this is a root bridge, and then you have a routing loop. Sorry, not a routing loop, you have a switching loop. And that traffic will be looping around the network, causing all sorts of mayhem. One thing I would like to note, that when we're configuring our Ether channels, you want to make sure that you bundle links in even numbers. So 2 links into an Ether channel, 4 links, 6 links, 8 links. The reason being is because when we use odd numbers or an odd number of links, the load balancing algorithm doesn't load balance evenly across the 3 links or the 5 links or the 7 links. If we use even numbers, then we're load balancing traffic in a more evenly distributed manner. And that's all there is to it. EtherChannel is that simple. Just take a whole bunch of links, combine them together into one logical link. The switches see the one logical link or the port channel interface. When it makes a forwarding decision, it says, I'm going to forward the traffic out of this port channel interface. When it comes to actually forwarding the traffic, guess what? I'm going to use an algorithm to decide which physical interface I'm going to forward the traffic out of. If you found this video useful, and you want to see more content like this, then please subscribe to my channel. In the next video, we're going to be looking at how to configure EtherChannel. Thank you very much for watching.